Okay, so we're on our second part looking at continuous random variables, and we've looked at the PDF and the CDF and how to calculate probabilities. So next thing we're going to look at is the expected value. So the definition is reasonably similar to the expected value of a discrete random variable. So again, we denote it by E of y, but this time instead of summing over all values, we're going to integrate. So we integrate all values of y, f of y. And we will say it exists as long as this is absolutely convergent. Okay? So let's go back to our example we've been working at. We've got the random variable y. It's basically, when it's less than 0, it's defined to be 0. When it's greater than 1, it's defined to be 0. But in between 0 and 1, we have that it is 3y squared, and we want to calculate the expected value of y. So let's do that. So first of all, we want the expected value of y. So by definition, we're going to integrate from minus infinity to infinity y f of y dy. Well, the first bit we will do from minus infinity to 0. That is going to be y times, and the PDF at that point is 0 dy, plus then we've got from 0 to 1 our y times by 3y squared dy, and then the final one from 1 to infinity is y times 0 dy. Well, notice first of all that y times 0 and y times 0 is 0, and the area under the constant 0 is just 0. So we know that this is 0 and this is 0. So we actually just care about 0 to 1, 3y cubed dy, which is 3y 4 over 4, and we're integrating from 0 to 1, which is 3 quarters. So the expected value of y is 3 quarters. So what if we want the expected value of a function? So we've looked at this already in the discrete case, but again, we've got a setup, we've got our y, we've got our PDF, and we've got some function of y, which is denoted by g of y, and we'll say it's a real valued function. Then the expected value of gy, instead of putting y as before, we put the gy, we times it by the PDF, and we integrate from minus infinity to infinity. And again, this has to be absolutely convergent. Well, we can use that idea now to define the variance. So remember, our expectation is a measure of location, our variance is a measure of spread. So to make the notation slightly easier, I know some people in consulting said, well, why do you keep using mu? It's just if I have the expected value of y here, you have an expectation gets a bit confusing. So let's call the expected value of y mu. There we are. And our variance is the expected value of y minus mu all squared. So because this is the expected value of a function, we put in our function there, we multiply it by our PDF, and we integrate over from minus infinity to infinity. Now, as I said, the variance is mathematically very nice, but its units, if we're looking at a random variable that has units, would be units squared. So if we want a measure of spread that's in the same units as the actual random variable, then we can take the square root, and we call that the standard deviation of y, and it's the positive square root. And the whole idea, mathematicians like variance, engineers, people using this, researchers like standard deviation, and you just flip between them. Let's think about a complicated function, an expectation of a function, and that's the moment generating function. Remember, this is a representation of our random variable that will produce our moments. And remember, the kth moment is e to the xk. So it's the expected value of our random variable to the power k. Very, very useful for getting things like expected values, variances, etc. So the moment generating function, MOT of continuous random variable, is still defined the same. It is the expected value of e to the ty. And we will look at the moment generating functions of various named random variables as we go through. Why do we care about moment generating functions? Well, it's a really nice property. Let's say we've got two CDFs. So we've got a random variable x and a random variable y. And we know that we've got a couple of constraints. The moment generating functions exist. And we do some calculations and we find that they have the same moment generating functions. And this is true for all t in some neighborhood of 0. Then you will find that they have the same CDF and hence they are the same random variable. And we use this property. I mean, the classic use of this property is the central limit theorem. In the central limit theorem, we actually use moment generating functions, we do some manipulations, and what we see at the end is the moment generating function of a normal distribution, so we know that it's asymptotically normal. So very, very useful. So that's everything in this video. Next time we're going to relook at the Chebyshev's inequality for continuous random variables, and I'm going to show you another proof of that that doesn't use the Markov inequality. Okay, see you next time.